Hello everyone. Welcome to lecture 2.3. In this lecture, we're going to introduce threads and cuda functions in cuda C. The objective of this lecture is for students to learn about cuda threads, which are the main mechanism for exploiting data parallelism. In particular, we will be explaining the hierarchical thread organization, how we can launch parallel execution in cuda, and also to understand the basics of how we can map thread index to data index in order to exploit parallelism. Before we introduce threads and kernel functions, I'd like to have a brief review of the data parallelism. Recall that data parallelism is a property of the program where different parts of the data can be computed independently of each other. In this example, the individual elements of vector C can be calculated independent of each other. This slide shows the CUDA execution model. We assume that we have a heterogeneous system with a host, which is a CPU, and one or more devices, which are GPUs. For each application, we will have the serial parts in host C code, and we will express the parallel parts in device single program multiple data kernel code. This concept is illustrated in a picture where we have a single thread executing serial code, and which is executed on host, and then we have a parallel section that will be executed by numerous threads on the GPU, and then we will go back into some kind of serial section executed on the host, and then parallel section executed on the GPU. We're going to explain some of the syntax that we have for the kernel launch later on. Though we're going to be writing our code in high-level language CUDA C, it will be important for us to understand how the compiler will translate these high-level language statements into instruction set architecture instructions, so that we can understand the performance behavior of our code. So this slide shows the 7-layer abstraction as described by Pat and Patel in their textbook, from bits and bytes to gates and beyond. At the top level, we can discuss and describe the computation in natural language. And then we can have a more rigorous description of the precise steps that we need to take in order to accomplish our computational goals, which will be the algorithm. And we can implement these precise steps of the algorithms in high-level languages such as C, C++, and so on. The compiler will take these high-level languages and then translate them into machine programs in instruction set architectures. And then the implementation in the hardware will take these instructions and execute them in terms of the logics and microarchitectural activities for implementing these instructions. And ultimately, all these things need to be implemented in circuits. And then finally, these circuits will be implemented in terms of the solid-state devices and electronics that flow through these solid-state devices. In order to fully understand the CUDA execution model and threading, we need to understand a little bit more about a program at the instruction set architecture level. At the instruction set architecture level, a program is a set of instructions stored in memory that can be read, interpreted, and executed by the hardware. Both CPUs and GPUs in a CUDA system are designed based on instruction sets, even though their instruction sets tend to be quite different. These program instructions operate on data stored in memory and or in registers. At runtime, a program at the instruction set architecture level will be executed by a processor. And the processor in the modern systems are designed according to a report written by John von Neumann in the 1940s. According to John von Neumann's design, a processor consists of a control unit and a processing unit. The control unit maintains a program counter which gives the address of the instruction to be executed next. And you can use that program counter to fetch the memory and derive an instruction from that address, and that instruction will be stored in the instruction register IR. And the control unit will decode the instruction in that IR and use the control signals to manipulate the resources in the processing unit, which has the ALU and register file in the picture. And these are the hardware resources we use in the first lecture series and when we show the difference between the CPU design and GPU design. The processing unit will access memory on top and the register file in the box to perform the computation. And this is really the foundation for understanding a thread. A thread is really a virtualized or abstracted von Neumann processor. Each thread can be thought of as a processor that's capable of decoding an instruction and having some execution resources and can access memory and register file. Now we can understand the concept of CUDA threads. In a CUDA system, the CUDA kernel is executed by a grid or array of threads. And here we show an array of threads of 256 threads. All the threads in a grid will run that same kernel code. And this is why we call this a single program, multiple data execution model. And sometimes you will hear the term single program, multiple threads, which is definitely a valid description. And each thread will have an index that it uses to compute the memory addresses and make control decisions. In the black box, we show that there is a variable called thread idx.x. And this is the thread index that we're referring to. So in the picture, each thread will have a different thread idx.x value. Thread 0 will have 0, thread 1 will have 1. That is, the value that a thread sees in this variable gives it the thread index. And these thread indices are pre-initialized for each thread in the system by the hardware. And these thread indices are pretty much like the jersey numbers for soccer players or local phone numbers for a cell phone. So we can see that in each thread, as long as each thread uses its thread index to access memory and make decision, each of them can potentially access unique memory locations and make unique decisions. CUDA threads are further organized into thread blocks. In this picture, we show n CUDA thread blocks. And on the left-hand side, we see thread block 0, and we still have 256 threads in that thread block. And the second one from the left is thread block 1, and so on. In order to uniquely identify the thread block that each thread belongs to, CUDA provides a pre-initialized variable called block IDX. And this variable, just like thread IDX, is pre-initialized by the hardware for the threads. So all the threads in thread block 0 will see a value of 0 in their thread block IDX.x variable. there's also another pre-initialized variable called block dim, and this variable gives the number of threads in each block. In this case, the value in block dim for this particular example is going to be 256. We can think about block IDX as a higher level index similar to the area code in the cell number. So in Champaign, the area code is 217. In New York, the area code is 201. So the same local number, let's say 3591234, means different cell phone, whether that depending on its area code. If it's 217.359.1234, it's a Champaign cell phone. And if it is 201.359.1234, that's a New York cell phone. So that's why if we take the block IDX.x times the block dim variable value and plus the thread IDX, we're essentially synthesizing a unique ID number that spans the entire thread namespace. So here in the example, keep in mind that thread block IDX .x0 is 0. So all the threads in block 0 will have the first term in that I expression 0. So the I values will be 0, 1, 2, 3, all the way to 255 for the I value, and they will be accessing A, B, and C elements from 0 to 255. And the thread block 1, recall that the block IDX value is 1. So, and the block dim value is 256. So all the I values in for threads in thread block 1 will be 256 plus their thread IDX value. So as a result, the I values for the thread block 1 is going to be 256, 257, all the way to 511, and so on. So as you can see, that this expression gives a linear coverage of a number space. We have for these two thread blocks, we cover all the way from 0 to 511, in a complete coverage of all the possible integer values. So this gives us every thread the I value, which is a globally unique index value that we can use to access a global address space, or a big array structure where we can use that to access every possible element in the structure, in the array. So in CUDA, the thread blocks are actually designed so that the threads can pull together their execution resources. One of the important difference between CUDA threads and CPU threads is that the CUDA threads tend to have very meager resource, but there are lots and lots of these threads executing in a particular hardware. So in some cases, we may need to have quite a bit more resource than what each thread can have access to in order to execute an application in a desirable speed. So in the CUDA hardware design, threads within a block can cooperate or share resources via shared memory. This is very fast, very high bandwidth shared memory, and also they can use atomic operations and barrier synchronization to coordinate their activities while they share resources to accomplish a particular common goal. And these threads are very intimately collaborating with each other through the execution. And we're going to see that this is critical in some of the advanced tiling algorithms and so on. Threads in different blocks do not interact. So you can think of every thread block as a focus team that is focusing on a particular region of the data structure, and all the threads collaborate closely to accomplish their joint goals. And now we are ready to look at a little bit more advanced concept involving the block index and thread index. We saw that the block index and thread index were in the form of block IDX.x and thread IDX.x. And you probably expected to see that there's block IDX.y, block IDX.z, which is indeed the case. And so the block and thread index variables are actually three-dimensional variables in CUDA. And so the point is most of the real-world models are either 2D or 3D. And so it's very convenient to have block indexes and thread indexes to be organized also in 2D and 3D, so that we can easily map the threads in a 2D or 3D form into a data structure that is intrinsically 2D or 3D. And this simplifies memory addressing when processing multidimensional data, such as images, such as a volume model in a physics model where we need to solve partial differential equations and so on. And so in the next several lectures, we're actually going to extend the CUDA execution model into these multi-dimensional situations, and give you more insight into how to write code to be able to process these real-world data structures much more efficiently. This concludes Module 2.3. Thank you.